Welcome back. This should be our last video of the semester. Again, we were talking about the importance of correlation and regression and when to use the regression line to make predictions and when not. Another thing that we want to talk about here is something called the marginal change. The marginal change is how much the variable changes as the other variable changes by 1 unit. So we're going to interpret this as how much the y variable changes as the x variable changes by 1 unit. Okay, and you will probably recognize this from previous math classes as simply the slope, the change in rise as the run changes by 1 unit. Now, in previous math classes, you probably saw the equation y equals mx plus b, where m was the slope, and that was the number that we multiplied onto the x value. Now, statisticians like to use the form y equals a plus bx. Note that the b here is the number that's multiplying the x, not the same as the b over here, which, if you remember, this b in slope-intercept form is what we call the y-intercept. So what we're going to do is use this guy b, and remember that he is the slope, okay, and he's going to be our marginal change. And if we remember our regression equation was y equals negative 72.87 plus 25.82 x, okay? And one more time, x was the number of people in the county measured in thousands, and y was the number of crimes committed in that county per year. Okay, so let's find and interpret the marginal change for our crime data. So the marginal change is simply going to be the slope. So, and what that tells me is as x goes up by 1, the y value is going to go up by 25.2. So for every increase of 1 in the x variable, but remember that 1 in the x variable stood for 1,000 people in the county, we expect or predict that the number of violent crimes, so actually it was just the number of crimes, will go up by 25.82. Now we're going to leave that as a decimal and not round it to 26 because we're talking about for every increase of 1,000 people. So we're going to leave that there. So if we increase by 5,000 people, then we expect the number of crimes to go up by 5 times 25.82, which will then give us, what would that give us? About 129 crimes in that year. So again, marginal change is simply the slope. What we call is the coefficient or the number multiplying onto the x value. All right, so let's go back to example 2 from our last activity. Professor Bedrero is jonesing for a convertible. I researched some prices and how many miles the car had been driven on some Mazda Miatas. And this is actual data from Kelley Blue Book in Utah. And so here's the miles driven and here's the cost. And this is exactly the same data that we had from last time. And remember that we did a hypothesis test on him. We checked our requirements that we had a random sample, that the scatter plot looks somewhat like a line. That's a stand-in for higher level stats classes where the x has to be normally distributed for the y and the y has to be normally distributed for the x. but if it looks something like a line for our introductory class, we'll call it good. And then if there are any outlier errors, we need to remove them. So for example, if someone were to accidentally type in negative 13,667, I don't think you can drive a car negative 13,000 miles. So not even in reverse. So you'd know that would be an error, so we would throw that guy out. So we did a hypothesis test, and we found out that our p-value was teeny tiny and less than the alpha, our level of significance. So we will reject H0 and conclude that there is enough evidence that there is a linear correlation between the number of miles driven and the cost of the car. So let's go ahead now. Oh, we even did it last time when we ran the lin-reg t test. It actually gave us the A and the B values for our regression equation, our predicting equation. So y equals 26908.92 minus 0.492 times x. Let me get that in there. There we go. So I've got that data, so I wouldn't goof things up. I put that data in list 5 and list 6. So let's go back in and do a new scatter plot. So let me move that up so we don't get as much glare. So let's do a scatter plot on list 5 and list 6. Okay. And we'll do a zoom stat. Oh, and we see that we've got extra stuff here. That's because this regression equation from the previous problem is still in there, so we probably ought to clear him out. Okay, now let's go back to our data. And that did look like a lot like a line. Let's go ahead and put that line in, 26908.92 minus 0.492 times the x variable. And let's graph that on our data here. Looks like it goes just under this one, a little bit above that one, and almost directly through this one right here. So let's go ahead and try to model that one on this guy right here. So if we were to draw that in using my straight edge, okay, we get this as our predictor equation. Okay, so we found the regression equation, and I'll rewrite him here on this page. So y equals 26908.92 minus 0.492 times x. Okay, and we graphed it on our activity, or plot from activity 1. So what we're going to do is we're going to use the regression equation to predict the cost of a car with 10,000 miles. So let's go back and get a visual of what's going on here. We're going to go to 10,000 miles, come up here and predict that, I'm not sure exactly, but it looks like it might be around $22,000 or $23,000. Well, to find out what it is exactly, we're just going to put 10,000 in for x, because remember that x was miles driven and y was cost, the independent variable and the dependent variable. The cost makes more sense to depend on the miles driven than the miles driven on the cost. Okay, so let's put that into our calculator. So let's do 26908.92 minus 0.492 times 10,000. And hey, my graph wasn't too bad. So I guessed it'd be around 22 or 23,000. So if we put that in, y equals 26908.92 minus 0.492 times 10,000, we get 21,958 and 92 cents. So almost $22,000. So I'm going to pause the video here, let you do C and D, and then we'll come back and check up on you here in just a second. And we're back. So hopefully you were able to use your regression equation to predict that the cost of the car with 20,000 miles would be basically $17,000, right around there. And again, the marginal change is the coefficient of the x, the number multiplying the x, which is our slope. And notice that this time our slope is negative because our line is going down. So that means for every additional mile driven, we expect the cost of the car to decrease because our slope is negative, and it's going to decrease by the amount of absolute value of this. So the decrease here picks up the negative on the slope. All right, we got this.